Hello students, welcome you back in the supplementary video lectures of the structure analysis one. So based on the feedback received from the couple of first sessions of the analysis of the truss, uh, I have moved forward to the another topic, and in today's session we are going to learn about the Macauly's method. So basically, we are discussing about this module since last number of sessions. That is nothing but displacement in beams. In a displacement of beams, there are number of methods. Out of that, in the today's session, we are going to discuss about the Macaulay's method and its a practice examples. So first of all, before going to the next part, there are some rules of the Macaulay's method. So first we have to discuss that what is the aim of this method? What is the main outcome of this method? So basically the Macaulay's method is a nothing but it's an extension of the double integration method. So let me recall the what was the basic concept behind the Macaulay's method. So basically in this we have to determine the slope and the displacement at various points in the determinate beams. So here let me go to the next part in which first it will be shown the basic deflected shape of the diagram, where you can see in the both the figure that because of the some load there is a some deflection at the different points, and the whatever tangent is made with that deflected shape, that is called as a slope of that particular point. So in this method, again like a double integration method, and also we have discussed about the Castigliano's theorem. We have to find out the slope and deflection at various point. So here there's a first of all this is the equation ei d2y by dx square equal to minus m. So where d2y by dx square is called as a curvature, ei that is a flexural rigidity, and m that is a moment. So this equation is called as a moment curvature relationship. Okay, now when we are going to integrate it. So here d2y by dx square is a become a dy by dx. So d2y by dx square is nothing but it's called as a curvature of the deflected shape, while when we are doing the integration it is become a dy by dx, while on the right hand side it is a become a integration m dx plus c1. So dy by dx is called as a slope, while another one more time it is a if you are going to integrate, so dy by dx is a become a y, which is a called as a deflection at any point. So basically what we are going to do in these examples that we have to do the two-time integration. So once we get the curvature equation, right? So we have to do the one-time integration. So we will get the slope equation, and one more time when we are going to integrate, so it will be give the generalized equation of the deflection. So there are some rules. So let me discuss about that rules first. So anyway, these rules, no need to remember it whenever we are go through the our practice examples. In that, these rules we have to follow. So these rules are nothing but the rules of the Macaulay's method. So first rule is always we have to take the origin on the extreme left hand side of the beam. That means whatever section we are considering the distance x, so that we have to start from the left origin only. Second is I take left clockwise movement as a positive and left anti-clockwise movement is a negative. Here, shagging hogging we don't have to see. So because we are taking the origin as a left hand side, so basically whatever moment you will see during the writing the equation, so we will see on the left hand side only. So all the clockwise movement we will consider positive and anti-clockwise movement as a negative. While calculating the slope and deflection, it is a convenient to use the unit as a kilonewton and meter. Whenever load and moment is a change at that section, we have to consider the new section and which we will show as a vertical dotted line. So that is a way of the representation in the Macaulay's method of the different section. The constant of the integration, when we are doing the one or two time integration, there will be some constant C1 and C2. Always they have that we have to write in the first part of the equation. Another is a x minus a quantity that we have to integrate, so it is a become a x minus a whole square by 2. Not we have to separate it x square by 2 minus ax, right? So there is again because of that there will be lots of advantage in the calculation, right? So we don't have to separate the bracket. A can be the any term in between the span, so it can be x minus 2, x minus 4, whatever uh, location will be there depend on the span. In case of the eccentric moment, generally what happens that whenever we have a force, so we are considering the moment equal to force into perpendicular distance. So when we have some moment, so we are not multiplying the distance, right? But in this case, what we have to do that we have to multiply the distance with x minus a raised to 0. In that manner, we have to write. So, but nothing but it's a x minus a raised to 0 is a become a 1 only. So it is a remain the moment, but that is again rule that whenever we are doing the integration, so we can know that at what location that moment is placed. Okay. And another is for any term x minus a less than 0. If that x minus a term will be become a negative, we don't have to see the square or cube or raised to 4, right? That entire term we don't have to see, but just x minus a term is become less than 0. So, or it is considered as a negative, then we don't have to consider that term. And last, one more, that is nothing but it's a UDL. Whenever there should be UDL, it should be continuous up to the right hand side. If it is not, then there is a one particular method that we will see in the form of the practice example. So again, as I have told you earlier, that we don't have to remember each and every rules anyway, because these rules we will going to apply in the all the practice example in the Macaulay's method. So let me go for the first practice example of the Macaulay's method. So what's the given data first? That use the Macaulay's method and determine the deflection at C and slope at support B and C. Okay. So there are a couple of things we have to find out. EI is given. There is a EI is called as a flexural rigidity. E is a modulus of elasticity, while I is a moment of inertia. So combinedly, it is given 4 into 10 raised to 4 kilonewton meter square. So here beam, simply supported beam is given where A is a hinge, B is a ruler. Entire span is loaded with a 15 kilonewton per meter UDL, while there is a eccentric moment of the 24 kilonewton meter clockwise moment is placed at the C, which is nothing but it's a 2 meter from the left hand side support. Now, first step is that it's a most simplest one which we have done number of times in the analysis of the beam. There is a nothing but it's a we have to find out the support reaction. So simply what we are going to do that we have to take a moment from M A. So what we will consider that VB into 6, right, plus 15 multiplied by 6 into 3 as it is a UDL, plus we have to consider this moment also, there is a plus 24. So based on that we will get the VB that is equal to 49 kilonewton. Now, what is the total load? It is a 15 multiplied by 6. So it's a 90. 90 minus 49. So it will be give the 41 kilonewton. So these are the basically our reaction. Okay, so based on this reaction only we can move ahead, right? So I hope it is a clear that because reaction is a quite basic steps and we have done number of times in the case of the beam, frame, arches and truss. Only the geometry is different. The way of the finding the reaction is remain same. So next we are going for the our actual method of the Macaulay's. So if you can see over here, okay, so if you can see over here, the reactions are shown. That is a left hand side is a 41 kilonewton, while right hand side is a 49 kilonewton. So what is the first step that we have to write the equation of the mx, which is the most important step. If the equation of the mx is correct, the rest of the all the things is just a mechanical calculation. So let me focus on the equation of the mx. So what we are going to do that we have to consider the different sections. Okay, wherever load is a changing or there is a change in the loading, so at that time we have to consider the new section. So let me consider the first section. Always we have to consider origin at the left hand support. So that is a not a support left hand side point. Suppose if it is a overhang, so it is not a thing that we have to see from the left support. We have to see the extreme left point as our origin. So let me take the first segment like this. The distance between the section to the first reaction or origin, that is nothing but x. So what we can see on the left hand side of the section. Okay, so there is a, yes, it is a clockwise we have to consider plus, so 41 into x, while minus this UDL, that is a 15 into x into x by 2. So let me write the equation of the mx, that is a 41 into x. Then we have to draw the one vertical line, then minus 15 x into x by 2. Now there is nothing is remaining in this section. So we have to move to the next one. Now there is a one moment at the C. So we have to just pass this moment. We have to pass this section. So next section will be in between the C to B. So now we have to forget about this earlier section and we'll go for this section. And again, the distance between the section to the origin is a X. Now what you can see on the left. So because already we have considered the 41 kilonewton and UDL on the left hand side. So what is the remaining thing? So that is a moment. So basically, as we have discussed in the rules, that in here when we are considering the moment, so it's a force into perpendicular distance is a moment, but here as you can see the eccentric moment, generally we are not multiplying the distance in the case of the moment, but as per the rule of the Macauly's method, what we have to do that here, what is the distance between the moment to the section? So total is a x, here up to the C, that is a 2. So what is the remaining distance? That is a x minus 2. So what as it is a clockwise moment, so what we can write that 24 x minus 2 raised to 0. So x minus 2 raised to 0 is a become a 1. So 24 remain as it is. But what is the significance of this term? That whenever we are going to do the integration, so it is a become a x minus 2 raised to 1. Then another time it will be give the x minus 2 raised to 2 by 2. So it will be show the location that at this location the moment is placed. So that will be going to consider while the finding the slope or deflection at particular points. So again I will repeat over here that here at this section whenever we have to consider the moment, so what we are to we have to consider that moment multiply the distance between the section and moment and rest to 0, because as we are doing the rest to 0, then and then it is a become a 1 and the moment will be remain as it is. Now second thing, that as we have seen the equation moment curvature relationship, so what is that? Ei d2y by dx square equal to minus mx. So this is our equation of the mx. So just we have to replace the sign. So it is a ei d2y by dx square equal to minus 41x. Then another section 15x square by 2. Then section minus 24x minus 2 raised to 0. Now we have to do the integration once. So from the curvature it will be give the slope. So what is the equation of the slope here? That x will be become a x square by 2. In the integration x square will be become x cube by 3, right? So it is in general we can say x raised to n is a become a x raised to n plus 1 by n plus 1. So here ei d2y by dx ei dy by dx, that is the equation of the slope. So 41x will be become a 41 x square by 2. There is another thing as we have seen in the rules, that whatever constant of the integration that we have to write in the first part of the section. So here the equation will be become minus 41 x square by 2 plus c1. Then there is a section 15 by 2. The integration of the x square will be become a x cube by 6. So denominator will be become a 15 x cube by 6. There is a 2 and there is an integration 3 will be multiplied. So 2 into 3 is a 6. Then another section, and what is the integration of the x minus 2 raised to 0? It's a n plus 1 by n plus 1. So it is a become a x minus 2 raised to 1 by 1. So it is a nothing but it's a minus 24x minus 2, right? So this is a nothing but it's a generalized equation of the slope. Now similarly, one more time, if you are doing the integration, it will be minus 41 x square will be become a x cube by 3. So it is a nothing but it's a 3 into 2, that will be become a 6. So it is a minus 41 x cube by 6 plus C1 will be constant, so C1x plus as we are doing the another time integration, so plus C2. Then there is a one section 15 x cube will be become x4 by 4. So 6 into 4, that is a 24. So 15 into x raised to 4 by 24. And the last section is a minus 24 x minus 2 will be become x minus 2 square by 2. So this is a, we can say, generalized equation of the deflection. So which is very much common, right? Only the important thing, as you have feel over here, there is a nothing but it is a equation of mx. So if the equation of the mx is a correct based on the your correct support reaction, so rest of the thing is just we have to do the couple of time integration. Now there is a one thing is missing here, that as you can see in this equation there is a some C1 and C2, right? So x is a variable quantity from the 0 to 6, but C1 and C2 we don't know, so that is a nothing but it's a depend on the boundary condition of the beam. So as you are aware about it, as we have discussed in the behavior of the beam in the lecture also, that whenever there is a some simply supported beam, so the generalized the deflected shape is of something like this. That means the deflection at the left hand side support is of 0, deflection at the right hand side support is also 0, and there is a some maximum deflection will be somewhere in the near to the middle or somewhere else, right? But the condition is that the deflection at the both the support will be 0, and that's a not that's our boundary condition. So what is our first boundary condition? That whenever the deflection will be 0 at the left hand support, so this is my x, the vertical will be my y. So what we can say, that when x equal to 0, which is nothing but it's a or point a, so x equal to 0, then what is the deflection? Y equal to 0. So if you are putting the y x equal to 0 and y equal to 0 in the terms of the deflection, so this is a 0. Second term, that is also 0. Okay, as this is a 0, right? This is also 0. Y is also 0. Now this one is also 0. When you are putting the 0 over here in place of the x, we don't have to see the square, right? So x minus 2, that means 0 minus 2, so it will become minus 2. So whenever x minus a term, which is a less than 0 in the any of the equation, we have to neglect that term in the calculation. Okay, again, I am telling to you that here we don't have to see the square or cube or any power. We have to see the x minus a term, right? As we are putting the x equal to 0, and as x minus a term is less than 0, so we have to consider, we don't have to consider that term. So what is the remaining? C2, and that is nothing but equal to 0. So that is our one of the constant of the integration. Now, next one, similarly, if you are considering the another boundary condition, there is a at the right hand side support, at the support B, my deflection is a 0. So what is the x equal to at that point? There is a 6 and y equal to 0. So that boundary condition we have to put in the equation of the deflection. So 0 minus 41, x will be become a 6 cube by 6 plus 6 into C1, C2 is a 0. Then 15 x4 by 24. So in place of the x, we will put the 6. Similarly, in the last part. So if you solve this equation, so you will get the C1, that is nothing but equal to 143. Okay. So now, based on this, you have to put the value of the C1 and C2. So what we will get? We will get the generalized equation of the slope and deflection. So dy by dx equal to minus 41 x square by 2 plus 143, as we have found out the C1, then 15 x cube by 6 and minus 24 x minus 2. Similarly, last term eiy, that is the equation of the deflection, eiy equal to minus 41 x cube by 6 plus 143 x, 15 x4 by 24, and as minus 24x minus 2 square by 2. So both of these equations are same, just we will find out the C1 and C2. Now these are the most generalized equation. If you have to find out the slope at any point, we have to just put the value in the equation of the slope. If you want to find out the deflection at any point between the A to B, so you have to put the value of the x in the equation of deflection. So let's try it. So here, as this is our equation of the slope, which we have find out in the previous step. So what we have to do that we have to find out the slope at C. So from the origin, if you see slope at the C, so x equal to 2, the origin. So here in the equation of the slope, we have to put the x equal to 2. So here we will get the yc, that is the slope at c, or we can sorry, theta c, that is the slope at c, and in place of the x we have to put the 2, right? So last term will be become a 0, and rest of the calculation if we do, so theta c will be become a something 81 by ei, and ei value is given in the initial data, that was a 4 into 10 raised to 4 kilonewton meter square, so we don't have to convert any unit. So finally we will get the answer is 2.02 into 10 raised to minus 3, and unit is a radian. Suppose if you have to find out this in the degree, so we have to multiply with a 180 and divide by pi. So it will be give the 0.12 degree. Again, when we have to convert radian to the degree, so we have to multiply 180 divide by pi. So you can check the answer. So which is a nothing but it will be show the slope at C. Next, if we have to find out the slope at B, so we can put the x equal to 6 as B is a 6 meter away from the origin, right? So x equal to 6 if you put in this equation, and if we do the calculation, so theta b, we will get the minus 151 by ei. So what is the indication of the minus sign over here, which is a nothing but as it is a nothing but it's kind of the rotation. So in the if we are considering the plus, that means it will be show the clockwise rotation, while the here it is a nothing but say in the anti-clockwise direction. And if we again convert this radian into degree, so it will be give the 0.22 degree. So what we can observe that generally slope will be maximum in the case of the simply supported beam at the supports only. Whenever the at whatever point when we get the maximum deflection, at that point slope will be zero, right? Because if you draw the tangent, so there is no rotation, there is no angle over there, so it will be slope is a zero. So similarly, suppose if you have to find out the slope at A, so we have to put the x equal to 0 in this equation, and we can get the slope at A. Now, if we talk about the deflection, so this was the equation of the generalized equation of the deflection from the previous step. You can check it. Now we have to find out the deflection at C. So similarly, like we have done in the slope, now we have to use the equation of the deflection, and we have to put the x equal to 2. And if we put the x equal to 2 in the entire equation, so we'll get the y is equal to 241.33 by EI. And again, if you put the value of the EI, so we'll get the answer in a meter, that is a 6.03 into 10 raised to minus 3 meter. And again, if you multiply with the 10 raised to 3, so it will be give the 6.03 mm. So that is a nothing but it's a deflection at C. So you have to observe over here that suppose if you put the x equal to 0 or x equal to 6, so it will be give the 0 deflection. So, what is the advantage of this method that based on the generalized equation, only based on the two equation, you can find out the slope and deflection at the number of points. Okay. Similarly, there is a one more example we'll see for the practice. And if you just refer this figure, there is a overhang beam. There is a one support hinge is given at A, while the roller is given B, and there is a UDL, partial UDL will be there in the half span of the span, okay, in the 2 meter, while there is a overhang portion of the 2 meter, and the point load 25 kilonewton is acting at the free end of the beam. So there is a EI value is given 23600 kilonewton per meter, kilonewton meter square, while we have to find out the slope at B and deflection at C and D. And as using the Macauly's method, like we have done in the previous step. So what is the first step? Yes, so we have to find out the support reaction. So it's very simple. It's very easier now to find out the support reaction, right? As you have done number of example practice earlier. So let's figure out here the support reaction. So let's take a moment from the A. So what we will get, that VB multiplied by 4, that is equal to 15 multiplied by 2, that is a UDL. The the net UDL that will be acting at the 1 meter. So what is the distance from the CG of the UDL to the A? That is a 2 plus 1. So that will be nothing but VB into 4, 15 multiplied by 2 into 3, and 25 multiplied by 6. So what we will get? VB equal to 60 kilonewton. Now what is the total load? That is a 15 into 2 plus 25. That is equal to VA plus VB. So if you do the summation of the vertical force is equal to 0. So what we will get? At VA equal to 15 into 2 plus 25 minus 60. So it will be give the minus 5. What is the indication of the minus? That we have earlier assumed, generally we are assumed that both the reactions are at upward direction. But here our VA is a minus. So that means our assumption is not correct and it will be in the downward direction. So let me show the reaction over here. So at A, the reaction is in downward direction, and at B, it will be uh, upward direction of the 60 kilonewton. Now, there is another rule which we have not used because it was not required in the previous example. That whenever there is a UDL is a given, so it must be end up to the right hand side, right? It doesn't matter where from where it is going to start. Okay, but suppose it will be going to start and it is completed up to the B point, then also we have it must be completed up to the right hand side portion. So in such cases, what we have to do, we have to extend that UDL. Okay, so here actually it is a starting from the C and it is ending up to the B point. So what we have to do, that we have to extend the same amount UDL up to the right hand side point. So it is all like this. Okay. Now, because in the actual beam there is no UDL in that span, so whatever UDL is added over here, that much we have to deduct in that particular span like this. Okay. So what is the significance of it? That whenever we are taking the section X, so we are we don't know that it will be going up to that X is going up to the which section. So here always this rule you have to keep remember, that always the UDL must complete up to the right hand side portion. If it is not going up to the right hand side portion, we have to extend the UDL up to the right hand side portion. Okay, so I will give you the another one example. That suppose uh, just a minute. So suppose if this is my beam, right, and suppose it is a, let's say, simply supported beam, you can assume. So this much is my UDL, right? Both the side there is some support. Okay. So in this case, what we have to do, that same way like here we have done, right? So we have to add this much of the same magnitude UDL we have to add. And as in the actual figure it is not there, so we have to deduct that much of the UDL. So whenever there is a equation of the MX we will write, so we have to consider both the UDL, right? Because upper UDL is anyway we are going to continue in the our section, but we have to consider the opposite UDL also, right? So let's write the equation of the MX over here. So in the first section, so we will cut in between the A to C. So it is something like this. And what we can see on the right left hand side of it, so it's a minus 5 into x, because if you see on the as reaction is a downward, so if you take a moment from the section, so you will take the uh, you will get the anti-clockwise movement. So it is a minus 5 into x. Now there is no further loading between the A to C. So we will go to the C to B where there is a actual UDL is going to start. So let's draw the section line, and we'll go for the another section, and it will be show the like X. So already we have considered the unit that 5 kilonewton load reaction. So we don't have to consider again. We will go for the UDL. And what is our load? That is a 15. At how much distance it is going to act? So here this is a 2 meter, right? A to C. So what is the remaining distance from the C to this section? Okay. So I will just highlight this is a 2 meter. This is the entire X. So what is the remaining distance? That is X minus 2. So what we have to consider that 15 multiplied by x minus 2 multiplied by x minus 2 by 2. Okay, so that x minus 2 will be, now x can be anything. It can be 2 to 6 any point, right? That means we are considering the entire UDL from the C to this D in the single one term. So what is the moment over here? So it is something like this: 15 into x minus 2 into x minus 2 by 2. So that is a minus 15 x minus 2 square by 2. Now, again, we will change the section. We are crossing the support. We are going to the overhang portion. So what we can write on the between the B to D. So this is my x. So what is the distance between the 60 kilonewton and the section. So entire distance is a 4 meter. So what is the remaining distance? That is a x minus 4. So 60 into x minus 4, which is a plus because that is a clockwise movement. And last, if you consider the this if you consider the violet portion, right, of the UDL, because upper green portion we have already considered in the second term, right, which is a x is contained from the 4 to 6 any value. So if you are considering that as a minus, so obviously this opposite UDL give the positive moment as it is in the acting in the opposite direction. So we'll consider the same distance like we have considered in the case of the point load, but it is a 15 multiplied by x minus 4 into x minus 4 by 2. So it is a 15x minus 4 square by 2. So there is only this much is the difference that you have to remember, that always the UDL must be completed up to the right hand side point. If it is not going to complete, then you have to add that much of the UDL and deduct that much of UDL. So remaining steps, if you see, that is the same. E I d2 by dx will equal to minus m. We have to do the integration. We have to change the sign of this. That is the equation of the curvature. Next step, we have to do the integration of it, which will give the slope. So in the first part of the integration, we have to write the integration constant. That is of x squared by 2 plus c1. 15 x minus 2 cubed by 6 minus 60 x minus 4 square by 2 and minus 15 x minus 4 cubed by 6. Last equation, that is again we have to do the integration. So it will be give the 5 x cubed by 6 plus c1x plus c2. Then second section, it is a 4 by 24, so it is a 15 x minus 2 raised to 4 by 24 minus 60 x minus 2 raised to 3 by 3, so it is a 6. So minus 60 x minus 2 cubed by 6 and minus 15 x minus 4 raised to 4 by 24. So this is our generalized equation of the dy by dx and y, which is a slope and deflection. But still C1 and C2 is a missing layer, so we have to put the boundary conditions. So if you put the first boundary condition in this, x equal to 0, y equal to 0, that means the deflection at the A will be nothing but it's a 0. So in this equation, if we put the x equal to 0, y equal to 0, so y equal to 0, this term will be 0, this term will be going to 0. Now if we reach up to this one, so 0 minus 2, so that is become a minus 2. So we have to neglect this term. Similarly, we have to neglect this term. Similarly, 0 minus 4, so it is again less than 0, so we have to neglect this term. So what is the remaining? That is a C2 is equal to 0. So like we have seen in the previous example, it's the same boundary condition and C2 is equal to 0. Similarly, there is another support. At this support also the deflection will be 0 because the beam is supported on this support. So it is a x equal to 4, the y equal to 0. So if you are going to put the x equal to 4 in the entire equation, so at the end you will get the C1 equal to 4.17. So if you are going to find the generalized equation, so it is something like this. Only in the equation of the slope, we are putting the C1 equal to 4.17. And this is the same remaining thing. Now we have to find out the slope at B. So we have to put the x equal to 4 in this equation. And if you are putting this one, so what we are getting, so you may do the detailed calculation and cross check your answer. And if you are not getting, so you may contact anytime for the how to calculate this so long calculation in the some easy way that we will see in the personally. So the answer is a minus 55.83. And if you put the value of the EI, so we will get the 2.36 into 10 raised to minus 3 radian. And if you multiply with a 180 by pi, so it will be give the 0.135 degree. Similarly, it is not asked, but if you are considering the additional step that what is a slope at A, so you have to just put the x equal to 0, which is a very easy. Why? Because if you put the x equal to 0, so you will get the theta A. First term is a 0, only 4.17 is remaining, and we don't have to consider the remaining portion because if you put the 0, so all the term will be x minus a is a less than 0. So we have to neglect all three terms. So the answer is a 4.17 by EI, and the final answer of the slope at A, that is nothing but 0.01 degree. Same way, if you write the equation of the deflection, generalized equation of the deflection, there is a 4.17x we have included, and remaining steps are as it is. So first, if you have to find out the deflection at C, so at that point x equal to 2, you have to put in the equation of the deflection. So we have to just consider up to this point because 2 minus 2 is a 0. So this two term will be 0. 2 minus 4, that is a less than 0. So we don't have to consider that last term. So what is the remaining? Only first two term. So what is the answer of this? You don't have to consider the remaining one. So it is a 15 by EI. And if you put the value of the EI, so you'll get the 0.63 mm. Same way, if you put the x equal to 6, so to get the deflection at D, so entire equation we have to consider, and if you put the value of the x equal to 6 in this, so you will get the minus 284.98, and which is indicating that it's a 12.07 mm. Now, what I have done here that based on this entire equation, if you put in the any kind of the software tool or any just simple in the Excel, so and if you change the vary the value of the x, so it will be give the all the value between the deflection at the any of the point. So same here, I have just draw the plot in the Excel by putting this equation. So what you can observe in this, that I have taken the interval of the 0.5. That's why the curve is very much smooth. So the first point, if you can observe that support A is at 0, support B is at the 4 meter. So the maximum the deflection the both the support. Second thing, that as there is no load between the 0 to 2 meter, so you can see the very less deflection, and there is a UDL in between the 2 to 4 meters. So there will be deflection as compared to the fan. We have find out the YC deflection, that is a 0.63 mm. So either you can do the manually or directly you can put in the any kind of the mathematical tool. So you are getting the same answer because it's a as it is a overhang, so it is going upward side. Otherwise, if it is a simply supported beam, then always the beam will be going on downward side always, right? So it is giving the 0.63 mm answer. While when we are going to the 4 to 6 meter, so as it is a overhang and there is a huge point load for 25 kilonewtons acting in the 2 meter span, so there is a huge deflection in the remaining portion. So you can see, you can compare the answer at the deflection at D, that is a minus 12.07, and here also you are getting the almost similar. So this is a nothing but it's a deflection profile, or we can say deflected shape of the this beam, which we can plot using in a simple manner with this one equation. So with this, we are going to end this session. What we have discussed today here, that it's about the displacement in a beam using Macauly's method with the help of the two examples. So there are some specific rules which anyway, when you are going to apply in the example, it will be easy to remember. So I suggest you that you should at least practice a couple of example, because this method is very much easier to understand and very much easy to calculate, because based on the one equation we can calculate the slope and deflection at number of points. And same this method concept again we are going to use in the derivation of the fixed beam in the structural analysis too. So with this we are going to end, but before going to end, I need to ask a couple of questions, kind of the review questions, so you have to think about it. So my first question is that what is the advantage of the this Macaulay's method as compared to whatever method you have learned up till now, like a Castigliano's theorem or double integration method. So what you understand from this, and what are the advantage you have uh, seen or you have observed in the Macaulay's method. And second question is that what is the limitation of the Macaulay's method? In which cases we can't use the Macaulay's method? So you have to think about these answers of these questions, and you may comment in the video, or you may contact with me anytime personally, and you can give the answer of it. So we are going to end this video over here. This is the kind of the additional resources, and based on your valuable feedback of the previous videos, I have decided to prepare this topic. So again, I will ask you to give the more feedback regarding the this video, which is a kind of the additional learning for you. And from this video, it is a kind of the learning for us also, that we can make such videos for the further more topics. So we will meet for the another topic in the future. Bye for all. And if you have more, like, give the feedback. So the links is always available with you. So please give your valuable feedback for this video also. Thank you so much.